Hello class and welcome. Today we're going to be going over chapter 1 on our Audio Engineering 101 handbook. Please make sure you've already read over that before watching the lecture. We're just going to touch over all of the fun stuff. Cool, so first off, what is sound? Vibrations in a pressure system. So of course, it requires a pressurized system for sound to actually work, because what's happening is the vibration of molecules. So if there's not any molecules, they can't vibrate off of one another, thusly there will not be any sound. So if there are molecules that are close in proximity, like here on Earth, we have a pressurized system, based on gravity, fun stuff. So ultimately with that, things are going to vibrate because they're all touching one another. So whenever I snap, we're going to hear that because it's creating a vibration that is going to vibrate the molecule next to it. It's going to vibrate the molecule next to it, so forth and so on, from the source to the listener. So in doing that vibration, it's a combination of compression and rarefaction. So compression is where the molecules are actually going to be condensed together. They're going to be pressed together. It's going to be high pressure, dense. The molecules going to be pressed together. Rarefaction is the separation of those molecules, where we're going to get low pressure, sparse. Our molecules are going to expand. So we're going to have a combination of rarefaction and compression. So a lot of times you'll see a sound wave drawn out like this here. You'll see this kind of what you kind of think of as like a wave. So whenever you see a sound wave drawn out like that, you're seeing actually a representation of compression, which would be the high amplitude portion, to rarefaction would be the low amplitude portion. So we're going to have compression, rarefaction. So we're going to see that drawn out. So a lot of times you're going to see us draw it out. Just easier to draw out, represent our sound wave in such a way than to actually draw it out like this. As you can tell, that would be pretty complex and hard to draw out, whereas this is much easier representation of what's actually going on. Cool. So the reason why that is going on like that is because sound is a longitudinal wave. A longitudinal wave is a wave in which particles of the medium move in a direction parallel to the direction of the wave. So it's going to require a medium, like sound. So sound is going to start at the source. It's going to be compressed, rarefacted, make its way all the way to the listener. Alternatively, a transverse wave, that's kind of like waves in an ocean or a light wave even. They're going to displace the medium. So the transverse wave, the displacement of the medium is perpendicular to the direction or propagation of the wave. So it can work in a vacuum. So we can think of like, a wave in the ocean. It's going to have these crests and troughs. They're going to go up and down. It's because it's displacing the medium being water. However, we're not displacing the medium with sound waves, because the molecule just kind of moves around. We aren't going to take the molecule from the source to the listener. We're just going to vibrate the molecule. He's going to vibrate the molecule next to him. He's going to vibrate the molecule next to him. Cool. So these sound waves, or really any wave in particular, is going to have 7 characteristics. So we're going to go over the 7 characteristics of a sound wave in particular. So those are going to include amplitude, frequency, velocity, wavelength, phase, harmonic content, and envelope. So let's go over each of those individually. Amplitude. So amplitude is going to represent the height of the sound wave. It's going to measure it's going to be measured in decibels, and it's going to represent the loudness or the volume. We can either boost or cut the volume or the amplitude. So as you see here, amplitude would just be the height of the sound wave. So that means we're getting a lot of compression here. We're getting rarefaction here. So the amount of actual compression is the amount of amplitude, and the amount of rarefaction is also the amplitude, just negative. Cool. Decibels or amplitude is measured in decibels. So there's some different examples of volumes that we can kind of use as a reference. So 0 decibels, that would be near silence, which is almost impossible here on Earth because of the gravity, lots of molecules, lots of things vibrating. In fact, just if you were to just take a moment, let just your room go quiet, on average, with your air conditioning running, sounds going on, it's going to be about 50 to 60 decibels just in that sort of space. So kind of room ambient anywhere from that 40 to 50. If you got your air conditioner on, it might even be up to 60. A whisper in a room, somewhere between 50 to 60 decibels. A typical conversation is somewhere between 60 to 75 decibels. A blender can get pretty loud at 80, 85 decibels, which is also, turns out, our optimal listening volume, which we'll go over why that is, but that's ultimately at about 85 decibels. Our highs, mids, and lows start to equal out a little bit. At 90 decibels, that's factory noise. Hearing damage can start to occur with long exposure. At about 100 decibels, be like a baby crying. 110 decibels, be a leaf blower, a car horn. 120 is actually the threshold of pain, so it can actually cause damage within a very small amount of time. A snare drum from about 1 foot away can actually get up to 140 decibels. So if you are a drummer, I do recommend using earplugs every time you practice. And a jet engine can get up to about 150 decibels. Cool, so that's amplitude. So let's go over frequency now. Frequency is the measure of how many cycles per second. So that's how many times do we get that compression rarefaction state, and how many times per second. So that's measured in frequency. Sometimes, or we call it hertz. Measured in hertz. And ultimately, it's just a gentleman that was able to figure that out for us. And it determines pitch. So the higher the frequency, the higher the pitch. The lower the frequency, the lower the pitch. A typical 1000 hertz would typically be represented as 1 kilohertz, the K for 1000. So 1 kilohertz would represent 1000 hertz. A below middle C is actually 440 hertz. Cycles is also known as cycles per second, or frequency is known as cycles per second. The average human hears between 20 cycles and 20,000 cycles per second. That's important. That will be on lots of the quizzes. Ultimately, it's just something to know. Humans can hear 20 to 20,000 cycles per second. And every time you double your frequency, you're going to go up an octave. So if we were to start at 440, if we were to double that, be 880, that would be still an A, just an octave in pitch. So frequency, a lot of times, is you're going to see it separated into what they call frequency bands. Lows, mids, and highs is the most popular way you're going to see that. A lot of times, you'll see it even broken out even beyond that, low mids, high mids. But just for our example today, lows, that's usually anywhere from 20 to 200 hertz. It's usually omnidirectional, very powerful, meaning that if a wave is actually cycling at such a low frequency, it's actually going to propagate in 360 degrees. It's going to leave the source and like a subwoofer, it's going to leave out 360 degrees, nice low end. Mids, those start about 200 hertz to 5 kilohertz. Those are less omnidirectional. Those start to become a little more directional, but those still kind of make their way around, maybe not 360 degrees, but they usually a little louder towards the front. Those are anywhere from 200 hertz to 500 kilohertz. Those are kind of classified as kind of in-your-face frequencies. As we listen to an example of that later, you're going to hear that those are going to vibrate. A lot of times they'll kind of start to hit your chest and make their way through your head, and you'll hear it vibrate all the way until you get to the highs. And the highs are going to feel like they're vibrating somewhere even above your head, because there's not really going to be vibrating your bones anymore, but you'll still be able to hear it and perceive it. So that's usually anywhere from 5 kilohertz to 20 kilohertz. There's usually highly directional, meaning if you have a 20 kilohertz coming out of a tweeter, it's usually going to be pretty straight line. They're usually pretty weak. Need to be classified as kind of bright or airy, because they just feel like they're just floating above your head. Cool. So those frequencies are actually, whenever we listen to different instruments, each instrument is going to be made up of different frequencies or different ranges of frequencies. So I like to use this frequency chart as a good way to get started whenever you first start mixing, of how to kind of separate and kind of, start giving kind of terms to those frequencies. So with this musical frequency chart, I've got a link here. You can follow that link. You see here like a bass guitar, kind of the weight of the bass guitar is going to be a low frequency, somewhere between 50 to 100 hertz. We're going to start to get a growl out of your bass at about the 500 hertz. You can start to get some snap out of a bass, even a little bit of a sheen it shows. With a kick drum, we can get a little punch around the 50 hertz, a little bit of boxiness around the 300. Start to get some clicking sounds around the 5 kilohertz. Just acoustic guitar, you can start to get kind of shows body around the 250 hertz. You start to get presence, just like you could with an organ or even a vocal sometimes. Start to get presence somewhere between that 2 to 5 kilohertz. So this is a cool chart. Take a look at it and follow the link. It's got some fun stuff to look at there. Cool. So let's move from frequency to velocity. Velocity is simply just how fast is this wave propagating. So sound travels at 1,130 feet per second at 68 degrees Fahrenheit through air molecules. So as the heat increase, or as the air gets hotter, the speed of your sound wave will actually increase, which is pretty cool. Cool. So wavelength. So with velocity, we can actually calculate the length of our wave. What we're talking about there is from our starting point to our highest compression level, our lowest compression level, back to our 0 point. So that full cycle is what they call a wavelength. So to complete a physical length of one cycle, again, is a wavelength. So wavelength is actually going to be calculated by taking our velocity divided by our frequency. So we figured out our velocity in feet per second. So if we were to take our hertz and divide that, because this is in feet per second, that's going to calculate in feet our wavelength. So a 30 hertz wave is actually going to be about 37 feet long. So just to complete one cycle of a 30 hertz wave, it's going to require a very big space. That's why we talk about bass traps and things of that nature, because sometimes these low frequencies are even too big to be created within one room, so they can overexert a room or cause things to vibrate off the wall and things of that nature. So just something to know. At about 300 hertz, that's about 3.76 feet. So, still pretty big wave. And a 3,000 hertz wave, or 3 kilohertz, is only about 0.376 feet. So, the waves start to get pretty small as we go up in frequency. Cool. Let's talk about phase. So phase is measured in degrees. It's used to measure the time relationship between two or more sound waves. So if we have effectively, let's say 2 mics and 1 source, well, each mic is going to get that source at a different phase. It may be at the beginning of its cycle. It may be somewhere in the middle of its cycle. And we found that if you keep things in phase, where the beginning of their cycles are together and they increase in amplitude and decrease in amplitude at the same time, we actually get what we call in phase, and the sound is able to increase in amplitude versus being out of phase, where you actually will decrease in amplitude. So ultimately, phase just designates a point in a sound wave cycle. We just some things to consider. That'd be phase cancellation. So if something is 180 degrees out of phase with itself, you're not going to hear it. 180 degree phase flip is a button that you can find on most consoles, where effectively you flip the button and it's going to flip the phase from where, instead of pushing the speaker or pulling the speaker, it's going to do the reverse. So if it was pushing, it will now pull, or vice versa. And you always want to be checking, if you're ever recording anything in stereo or multiple mics on a single source, you want to always be checking it in mono to make sure that it may be 180 degrees out of phase from the left and the right, and they may sound fine in an acoustic space, but as soon as you go into a mono space where that left and right are coming out the same speaker, if they're 180 degrees out of phase, you may not get any sound. So it's always good to check your mixes in mono to make sure that you're not going to lose anything. Ultimately, phase needs consideration for any sort of stereo miking technique, or any technique that you're using multiple mics on a single source. Harmonic content, also known as timbre, contains octaves, partials, and overtones. So every time, let's just take a bass guitar for example. Every time the bass guitar, the string is struck, we get our fundamental frequency. That's the lowest frequency. However, we don't just get that one frequency. We also get a whole load of other information, what we call our harmonic content. It's effectively, this is our fundamental. If this was our fundamental here, we're able to see that we can get third order, fifth order, even more. We can second order. All sorts of these different harmonics are just lower amplitude, still vibrating, but they're vibrating based on the fundamental. So if we know the fundamental, we can actually calculate our harmonics, which is pretty neat. So let's see, to do that, we're going to multiply our fundamental by the harmonic number we're trying to find. So if our fundamental is 41 hertz, we can figure out our second harmonic by multiplying 41 times 2 to get 82. Our third harmonic, 41 times 3, 123. So just as a simple example, if our fundamental is 100 hertz, we want to figure out the third harmonic, that would be 300 cycles per second. One thing you need to know, especially for the quizzes, is that harmonic content is one of two waveform characteristics that help humans differentiate one instrument from another. Harmonic content is the reason why is because even though it's in relation to the fundamental as far as our math goes, every instrument is going to have a different harmonic content based as far as what amplitude are these guys going to be at. And so because every instrument has its own harmonic content, we're able to differentiate, my voice from, say, your voice, because the shape of my voice box, the way that I speak, those things create different harmonics than you might. Even though if we were to both sing, a fundamental of 200 hertz, our harmonic content would still be different. Even though it might be the same numbers, same frequencies, amplitudes would be different, and so thusly we can tell the difference between my voice and yours based on the harmonic content. Why an acoustic bass sounds different than an electric bass. So envelope is the other characteristic we need. It also helps us differentiate one instrument from another. Envelope is actually effectively, it's kind of the sound over time. So what we're looking at is time and amplitude, and we're talking cycles per second. So there's lots of cycles in here, but those cycles are going to effectively have an envelope, which is from start to finish. Every word we have has consonants in it. So every consonant actually has its own envelope, which is every time you have to open your mouth, that's your own envelope. So every struck of the bass guitar, every piano play, whatever it may be, whatever the instrument may be, every note effectively has its own envelope. And so this envelope is consistent of attack, decay, sustain, and release. So a couple of these are actually time relationships. So attack is the amount of time it takes for your signal to go from nothing to its loudest amplitude. So that's your attack time. Decay is how long it takes to get from that peak amplitude down to what they call the sustain level. The sustain level is based on amplitude, and it's actually just a volume at which the instrument starts to level out for a little bit before it is released. And release, again, is time. It's just the amount of time it takes to go from that sustain level back down to nothing. So let's watch a quick video that has been put together already for us that has a lot of good examples. Let's take a look at that real quick.
Hey, what's up? It's Wick for Wikimedia Tutorials, and today I'm going to talk about the envelope. The envelope of a sound describes the way that the amplitude varies over time. Simply put, how the sound gets louder and softer over time. The envelope of a sound is divided into 4 sections: the attack, decay, sustain, and release. This makes up the abbreviation ADSR, which you will find on a lot of audio gear, like on samplers and synthesizers. The attack is the time that it takes to go from generating the sound until it reaches its full amplitude. Most sounds have got a short attack time, especially drum sounds and picked sounds. Some sounds, for example generated by a bow, will have a longer attack time, like a violin or a cello. The decay is the time it takes for the level to drop to the sustained level when the attack time has passed. The sustain is the level at which the amplitude more or less stabilizes. Longer sustained sounds, like again a cello, have a much longer sustain than a short or a transient sound like a snare drum. The release is the time it takes to go from the sustained level into silence. The release is really the tail of the sound. Let's take a closer look at the envelope of different sounds, and let's also listen to what they sound like. Here is the envelope of a snare drum recording. You can see it's really short, so we categorize this as a transient sound. You can see it has a really short attack time. This is the envelope of a kick drum. You can see it's also a transient sound and it's got a really short attack time. Let's take a look at the envelope of a violin. I've got two different envelopes here. This one is showing a longer tone, and these are obviously a lot shorter. A guitar can have a really short envelope when it's being played with a pick, but it can also have a much longer attack when it's being played with fingers and playing a chord. Let's take a look at these two envelopes and listen to these. This is the envelope of a saxophone, and it can create a lot more crazy curved envelopes than this, but this is a pretty good example. Let's take a listen at this one. This is the envelope of a trombone, and let's take a listen at that. The cool thing with these instruments is really the way that you play them will have a great influence on the envelope. Let's take a look at this flute envelope right here, and you should probably be able to recognize this tune. A piano has a sustain pedal, so it can actually increase the sustain, and I've got a recording here in which we at the end let go the sustain pedal, so you can hear the great influence of the pedal. Note that depending on the sound that you're working with and the location that this sound has been recorded at, the release can contain some of the natural reverb of the acoustics of the location. So that's already blended in this tail, and it's not part of the actual release of the instrument, but it's been added by the room. Trying a different microphone or a different microphone position, like close micing it, would make a big difference on the release tail of the sounds that we record. You will commonly find these names on samplers or on synthesizers where we can shape the sound. And if we want to shape the sound of something that we've already got recorded, we can use gates and compressors to still shape some of the envelope of a sound. So this was explaining the envelope for today. I'm Wick for Wikimedia Tutorials, and I hope you've learned something today. If you want to know more about the gates or the compressors or equalizers, filters, you should check out some of the other videos on my channel. Don't forget to subscribe, and I hope to see y'all soon.
Cool. Cool. So that's envelope. So again, that's just another characteristic that we use to differentiate one instrument from another. That's why we can tell the difference between a kick drum and a bass guitar. You know, they have a different envelope and different harmonic content. Cool. So that is the 7 characteristics of sound. Let's go into noise. So as a sound engineer, noise is kind of a bit of a problem. It's something we want to keep as low as possible, especially if we don't want it. So noise is sometimes just the ambience of a room. It could be an air conditioning vent. It could be, you know, kids somewhere down the street. You know, it's just things you want to keep out of your recording. So we call our noise floor. That's just what we want to keep as low as possible. So sometimes we refer to it as signal to noise ratio. We want to keep our signal high and our noise low. So the higher the ratio of signal, the better. Obviously, analog and digital have different headrooms. Digital, turns out, has a really high headroom. So you have to really get loud signal in order for it to distort. So that means you can actually keep your signal really high above the noise floor, which is one thing why people really love digital so much. Analog itself has its own noise floor, and it has a lower headroom, so thusly it actually has quite a bit more noise in it. But it has that classic sound. Noise, again, it's usually unwanted and sometimes non-repeating, and we just want to do our best as audio engineers to keep it to a minimum. Distortion. Distortion is another thing that, unless we want it, we want to keep it to a minimum. So distortion, sometimes characterized as dirty, aggressive, or in your face. It's usually caused by levels being too hot. Sometimes it can be caused by tubes or even bad electronics. This particular example is showing what it's like if you actually digitally clip, which we don't want to do, because what happens when we digitally clip is, like an analog signal, if we go above the headroom of the digital recorder, we aren't going to actually be able to get any of this information. This red would be our information. So if we're below, you can see that we get our, all of our headroom. We can tell exactly what that wave is supposed to sound like. However, if we turn it up too loud and we hit that headroom, then all of a sudden we're going to lose all of this information. So to avoid losing that information, we want to make sure that we're avoiding clipping, especially when we're recording digitally. If we're recording in analog or tubes or with a distortion pedal or something where we want distortion, that's cool. But if we're trying to avoid distortion, and especially digital distortion, because digital distortion doesn't sound good because you're really just losing information, it can actually come across as like a kind of sound. It's not good. So we just want to avoid it in every time we can in a digital format. Cool. Let's go over simple versus complex waves. So a typical wave, we get our compression, rarefaction, compression, rarefaction. Well, this is a sine wave. This is very common. People like to see them drawn out. They just look good. But not every wave is made of sine waves. Some are square waves, which is effectively signal on, signal off, signal on, signal off, signal on, signal off. Ramp is where we ramp up to high compression levels and it drops to no compression, ramps up to high compression levels, drops to no compression, or lead to rarefaction. And the reverse is a sawtooth, and then a triangular wave. So each of these kind of have their own different sounds. So again, I've got a quick simple video that kind of has those broken down. But the big deal that I want y'all to see in this video is complex waves. I want y'all to see how whenever these waves combine, they start to look more complex. Very, very quickly. We'll go from a sine wave where if we just add another sine wave even, all of a sudden this sine wave doesn't look anything like a sine wave. So let's check that out real quick.
Hey, what's up? It's Wick for Wikimedia Tutorials, and today I'm going to take a look at simple waveforms and how we can combine simple waveforms to make more complex waveforms. What I've loaded up is a 1 Hz frequency in Adobe Audition, and I'm going to see the behavior when we're going to add this to another frequency. So you can see this duration of this clip is exactly 1 second, and we've got one completed oscillation. Therefore, we talk about a 1 Hz frequency. If I'm going to look at the 2 Hz, you can see this is also the duration of 1 second, and this has 2 completed cycles in 1 second. Therefore, it is a 2 Hz frequency. If we go to the 3 Hz, you can see we've got 3 completed cycles in 1 second. I'm going to go to the 1 Hz, and I'm going to copy this. So I'm going to go to Edit, I'm going to copy it, and now I'm going to go to my 2 Hz, and I'm going to select the whole clip, edit, and mix paste this at the same amplitude. And you can see this created a much more complex waveform, and this doesn't look like the sine wave. So this is the combination of these two sines combined. So let me undo that, and let me add this 1 Hz frequency to the 3 Hz frequency. So I'm going to go to Edit, Mix, Paste. You can still see the shape of that 1 Hz frequency here, but it has been modulated by that 3 Hz frequency. They're both at the same amplitude, so that's something normally you wouldn't really find, but you can see how the behavior is when we add these frequencies together. Besides the simple sine wave that we've just seen, other simple waveforms are, for example, a square wave. A square wave just looks like a square, as the name kind of suggests, and it looks, when we zoom in, pretty much like this. So just a square. If we play that back, this is a square wave at 220 Hz. I'm gonna play that back. Compared with the sine at 220 Hz. You could say that the square sounds a lot more aggressive. We also have a triangle wave. Let me zoom in on that. You can see this is a triangle-shaped waveform, also at 220 Hz. So it's the same frequency and it sounds like so. Again, it's 220 Hz, so we can clearly hear the pitch, but again, it sounds a little bit more aggressive than the sine wave. So we can actually combine, let's say, square waves as well. Here I've combined a 220 plus a 440 Hz square wave. But we can see the addition of these two. So I've got the square of 220 here. And I've got the square of 440 somewhere else, right here. And this is just the output of both of these combined. And that looks like so. And it sounds like so. So these simple waveforms are actually the basics of synthesizers, where we can actually combine simple waveforms and manipulate them, modulate them, filter them, and do a lot of crazy stuff with them to create synthetically made up sounds just with simple waveforms. When we combine a square waveform with a triangle waveform, I've used the same frequency here, you can see this is the result of the output of these two signals combined. You can see it still has the character of the triangle or the sawtooth waveform, and also it has that real distinct shape of the square waveform. So this is really the combination of both of these. Let me just lower the amplitude a little bit. So I'm going to go to my amplitude and put it on 75%, and I'm going to use 110 Hz. So I'm not going to use the same frequency. I'm going to use an octave lower. I'm going to copy this sine wave at 110 Hz, and I'm going to combine that with the 220 Hz waves of the square and the triangle already combined. So we're basically combining three waveforms. So let me paste that in. Let's go to edit, mix paste. Use that at 75%. It's already getting a lot louder. You can see this is really giving some complex waveforms. It still repeats over time because we're still using these simple waveforms, but you can see this is already starting to create some really interesting looking waves. So this sounds a lot different, and it's like synthesis again. So let's take a look at some other interesting behavior of waves, and I'm gonna use the sine wave again, and I've created this 55 Hz sine wave. And I've got a 880 Hz sine wave as well. This is the same duration that I'm zoomed in on, as you can see right here in the corner. And if we combine this 55 with the 880 Hz sine wave, we get this as a result. So we can see that basically the lead or the main frequency is still carrying here. You can see that this is really that same sine wave as we see here. But it really added this 880 Hz frequency to this 55 Hz frequency, and this gives this as a result. So what we could do is, let me just use a 1 Hz frequency. So I'm going to copy this 880 Hz frequency. I'm going to select all of it. I'm going to go to edit, copy it, and then I'm going to open up my 1 Hz, and I'm going to edit, mix paste that in here. You can see clearly that this 1 Hz frequency is like the carrier frequency, and if we zoom in, you can see it's been modulated because it's got all these smaller sine waves in it. It's like a really thick sine wave. In the next video, I'm gonna take a look at more of the harmonic content and what harmonics do.
Cool. So that's exciting. So effectively, that's just simple into complex. So not all waves are simple, as you can see, that's kind of more of a synthesizer kind of thing. In audio, most of the time we're going to be using something that's coming from a microphone or musical or voice or something like that, which are complex waves in and of themselves. Cool. So let's go over analog versus digital. So analog is fun because effectively analog is pretty much just a recreation of the original wave. We're just using analog voltages to do so. Digital, however, is using zeros and ones to recreate the analog voltages. So let's go over how they do that. So digitally, we're going to use sample rate and bit depth. Let's go over sample rate first. Sample rate is going to determine the frequency response. So that's going to determine just how many cycles per second can we actually measure with our digital recorder. So it's going to sample rate is the number of samples per second. So a standard audio CD is actually going to sample 44.1 thousand cycles per second. So our samples per second. So for every second, the CD is going to be taking just a snapshot of the voltage, saying just how much voltage is there. Every 44.1 or 44.1 thousand times a second. So that's a whole lot of samples. As you can imagine, that's a whole lot of representation to create the frequency. But we found the reason why they sample 44.1 thousand times is because they want to make sure they're at least sampling enough to capture the positive information and the negative information needed to recreate what humans need to perceive audio, which again is 20 to 20,000 cycles per second. So they were able to calculate the Nyquist theorem. The Nyquist theorem is cool. It states that the signal's sample rate must be at least 2 times greater than the highest desired frequency. So if we were to sample at 44.1 thousand samples per second, we're going to be able to represent up to 22.5 cycles per second in hertz. How many frequencies? So that means that humans, again, we can only hear 20 to 20,000 cycles per second. So CD quality, effectively, they made sure we had at least all that humans needed. So we can capture up to 22.5 cycles per second. A lot of times, though, nowadays, a super audio CD uses 48,000 cycles per second, because that can represent up to 24,000 cycles per second. 96 kilohertz can represent up to 48,000 cycles per second, and 192 kilohertz can represent up to 96,000 cycles per second. Usually, whenever you're doing something with this high of a sample rate, because humans don't need to hear this high up, as you can imagine. However, let's say we want to slow down or speed up the song, or we wanted to change the pitch. So usually nowadays everyone's doing pitch correction, auto tune. So they're using these higher sample rates. So that way, as they are manipulating the frequency in such a way, they're able to maintain all of its integrity, which is cool. Cool. So that sample rate, again, which is how many samples per second, in the order of thousands, per second, at least over 44.1 thousand samples per second to get audio that humans can record. We also have bit depth. Bit depth is going to determine our dynamic range. That's the difference between the loudest voltages and the softest voltages. So it's going to ultimately, bit depth is the number of values that can be used to describe the range of voltages in an analog signal. So an 8-bit would actually give us 256 steps. So that's 256 variables between our softest and our loudest, because that's 8 different, it's either on or offs, so that's 256 different values that can be represented with 8 different on or offs. So because we've got 8-bit, 8-bit was cool. That was fun for like video games and stuff. You just need to kind of like make some like coin sounds. Everything's the same volume. However, CD quality, if you notice, quite a bit more steps. CD quality is 16-bit. 16-bit, 44.1 thousand samples per second. So in a 16-bit format, we can get up to 65,536 variables between our loudest point and our softest point. So it's quite a bit of variables there. 24-bit, as you can see, steps it up even more. 16 million steps, so quite a bit. So that super audio CD is 24-bit 48K, standard CD 16-bit 44.1 thousand samples per second. Cool. So let's go over some of the pros and cons of analog. Analog, again, is fun. It's sound that is recorded and reproduced as voltage levels. Whenever we talk about we'll go over our next class, we'll go over how we actually create those voltages with a microphone. However, the pros of an analog signal is that it usually has better frequency response because it's able to capture everything, so if the violin vibrated at 90 cycle or 90,000 cycles per second, we could pick that up, because it's just picking it up. It doesn't have to have a sample rate that's sampling enough times per second because it's just putting that voltage down. Usually has softens the transients. Transients are at the beginning of all your envelopes. There's a transient, which is that your attack and decay time. During that time, there's that spike up and down. That's what we call our transient. It's the beginning of every envelope, and sometimes those can be more dramatic than other times. And having a softer one means that you can actually get more sustained level. You don't have to worry about that little transient clipping you out. So that's another advantage of analog. Usually can be hit harder, usually resulting in more warmth or natural sounding compression. It's a very classic tone. And of course, it adds roundness in that warmth that we talked about. Some of the cons: it has a worse dynamic range, meaning the difference between the loud parts and the soft parts. Because we talked about that headroom and the noise floor. Because it has a higher noise floor and a lower headroom, there's not as much of a difference between your loud parts and soft parts. Usually always has a hiss. Just naturally, the tape machine itself, just the mechanics of it, causes a hiss. It's usually very expensive. The editing is much harder than it is in a digital format. Very cumbersome because tape machines get very big. It usually takes a few people to move them around. And of course, the conversion to digital is almost inevitable at this point because everyone's putting their stuff on either a CD or YouTube or some sort of digital format. Cool. Let's go over some pros and cons of digital. So again, digital is just sound that is recorded as binary data, just zeros and ones. That's why we have to have so many bits per sample, and then why we have to sample so many times per second. Some of the pros: it's easier editing or recall. You can have presets, all that fun stuff. It's very efficient. Better transients, meaning that it's not going to soften those transients on its own. So you have to do that yourself with some sort of maybe like a compressor or something. Noise floor is almost non-existent because of how much headroom it has. It's very compact, convenient. Everyone can there's recording devices on your phone nowadays. We got handheld recording devices. We've everyone's got a laptop nowadays. Most folks have a laptop nowadays where you can put your digital audio workspace on there. The storage costs are much lower because hard drives are much more affordable than a tape machine would be, or tape for a tape machine. And of course, the demand is much higher for digital because everyone's ultimately converting to digital. Some of the cons: the tonal quality can sometimes be considered thin or bright because there's nothing there to warm it up. That's why there are some plugins out there nowadays that can provide that warmth. And sometimes with digital, you can create lossy files. We'll get into that here in a little bit, but a lossy file means that you're spending all this time and energy to create all these zeros and ones, and then a lossy file just throws out half of them. So we want to use what they call lossless files. We'll talk about that here in a little bit. And of course, a digital system can crash, more likely to crash than an analog system would. But they're getting much better, and as long as you have a good hard drive and you're not overloading your computer, crashes have become much better than they used to be. Cool. So let's talk about lossless versus lossy file types. So digital, again, we're creating this binary data, zeros and ones. So a typical wave file or audio file that's in a digital format is what we call lossless. That means it's going to retain all of that binary information even when we compress it or zip it down. So an example of that would be an AIFF, a wave file, a FLAC, or ALAC. These are cool. each of these, if you were to import them into your DAW, are going to retain all of the zeros and ones that were originally there when the piece was originally made. All of the bits, all of the correct amount of samples. That'll all be there. Alternatively, we have what they call lossy. Lossy is where the data is compressed by throwing out binary information that is deemed unnecessary. That's like an MP3 or an MP4 or Og Vorbis. There's other lossy file types out there, but I recommend staying away from them unless you just need to send a quick email or something like that. But if as an audio engineer, if you're going to be editing it or using it within your piece, I recommend, if you have the option, to use lossless. Cool. So I think that made us all the way to the end of our first lecture. So again, I do appreciate y'all, and please bring any questions you have to our class where we'll go over this lecture. And also want to remind y'all that quiz 1 will be due next time. So we want to make sure y'all follow this link. Of course, all of this lecture will be posted on Blackboard, so you'll be able to follow that. It's going to be a PDF. All these links will be there and active. I'll also create a link in Blackboard for you to follow on your own. However, let's just follow it real quick just to get there. This is the quiz website. It corresponds with the book. So for the quizzes, we're just going to have you come here to quizzes. There's effectively, we've got chapters 1 through 10, and even the final exam is already there. So you'll just launch the quiz, take the exam, and effectively once you get to the end, if you didn't get 100, please just try it again, because what I want you to do is submit to me your 100. Once you've got to the end, you've got that 100, get a screenshot and email that over, because then I will get that in your Blackboard as your 100 for that quiz. Cool and sweet. Please let me know if y'all have any questions. It's always a pleasure, and I look forward to seeing you all soon. Thanks again.